Alright, so this ice sheet's all about trying to find the matrix representation for linear transformations. So we've got three different transformations here, kind of going from easiest to most difficult. And kind of for the best results and kind of feedback for yourself on how you're doing, what I want you guys to do is try to get through as much of this as you can before watching this video. And then if you're stuck, or if you just want to double check your work and make sure you're on the right track, then come back and watch this. Alright, so we're going to start with this first one. We want to go ahead and define a linear transformation from P2 to P1, so polynomials of degree at most 2 to polynomials of degree at most 1, where when we transform an ax squared plus bx plus c, we get 2ax plus b as a result. Some of you may know this from Calc 1 as being a derivative of a degree 2 polynomial. So what we're going to do is we're going to start off by finding our basis for P2, which we're going to call b sub v. And I'll make it x squared, x, and 1. And our basis for P1, which we'll call b sub w, which is going to be x and 1. Okay, so maybe something that would be fun to do in the discussion board is, what if you switched the order of these bases? So made it 1x, x squared, and 1 and x. What happens to your matrix when you do that? What does that matrix look like? Maybe it might be fun to play around with. All right, so what we're going to do then is we're going to transform these vectors using this transformation and then write the output in terms of this basis. So we want to take and transform x squared, write it in terms of the basis for our codomain. When we transform x squared, because we're looking at x squared compared to ax squared plus bx plus c, the a part's going to be 1, b is 0, and c is 0. So what we should end up getting is just 2x, which we want to write in terms of our codomain's basis, which is going to give us 2x plus 0, so 2, 0. Okay, we need to also transform x and write it with respect to the basis for our codomain. So transform x using this transformation. Here, because we're comparing x to ax squared plus bx plus c, you can find pretty quickly that a is 0, b is 1, and c is 0. So plugging that in, we get an output of 1, which we need to then write with respect to the basis for the codomain. And so we'll get 0x plus 1 using this basis to write what this is going to be. And last but not least, we need to transform our last basis element from our domain, 1, and then write it as a coordinate vector with respect to this basis. So if we transform 1, comparing 1 to ax squared plus bx plus c lets us know that a is 0, b is 0, and c is 1. And so we just get 0 as an output. So we need to write 0 as a coordinate vector with respect to this basis, and so we get 0, 0. So that means our matrix is going to be found by taking these columns, or these vectors, and writing them as the columns of the matrix. So the first column will be 2, 0, next column will be 0, 1, the last column will be 0, 0. All right, 1 down, 2 to go. Let's keep moving on. So let's say we wanted to go and take this transformation from P2 to P1 and find a matrix form for this transformation. What we're going to do is we'll start off with a basis for P2 and for P1. So I'm going to use the same bases I used before. Again, if you want to switch the order and maybe talk about what you got in the comments on the discussion board, that is totally fine. I encourage you to do that. It's good practice. So we've got our bases. Now we need to transform each of these vectors from our domain basis and write them eventually as coordinate vectors with respect to our basis for our codomain. So I'm just going to kind of do a little bit of prep writing setup over here. Space out my room on the page. Okay, so first and foremost, we want to transform x squared using this transformation. So again, if we compare x squared to ax squared plus bx plus c, we see that a will be 1, b will be 0, and c will be 0. plugging in 1 for A and 0 for anything, the B and the C, we'll get 1 minus 0, so just 1x, plus 1 minus 0, so just x plus 1. So you need to take x plus 1 and write that with respect to this basis. So we're saying we have 1x plus 1, so it'll just be the vector 1, 1. Next, we want to go ahead and transform x using this transformation. So here, if we compare x to ax squared plus bx plus c, we see pretty quickly that a is 0, b is 1, and c is 0. And so plugging in 0 for a and c and 1 for b, we get 0 minus 2x, so negative 2x, plus 0 minus 0, so just negative 2x will be our total transformation value, and we need to write that in terms of this basis for our codomain. So then trying to write negative 2x in terms of x and 1, we'll have negative 2 times x plus 0 times 1. So we get negative 2, 0 as an output. And then last but not least, we want to take 1 and transform it using this transformation. So here, if we compare 1 to ax squared plus bx plus c, a has to be 0, b has to be 0, and c has to be 1. So that means we end up with 0x, so just 0, plus 0 minus 1. So in the end, we just get negative 1 as an output to that transformation. We want to write that with respect to this basis here. So we have 0x minus 1. And so that will be what that is in terms of our basis for our codomain. And so our matrix is going to end up being 1, 1, negative 2, 0, 0, negative 1. Okay, so then we will move on to the last problem here. So this example is going to be a bit more challenging. So let's say we had this vector space, and our codomain is going to be, this is going to be our domain. Our codomain is just M2 by 2. We want to go ahead and create a transformation going from this complicated basis, domain space, which is a subspace that we'll have to figure out how to create a basis for, to just M2 by 2. So Archer seems to think that a basis for V is going to be 1, negative 1, 1, and 0, 1, 1. If there's anything you probably have learned if you paid attention to anything involving Archer and Eva, Archer is usually on the right track but not quite there. So let's talk about what this basis is going to actually be for V. So we say that V is the set of all ax squared plus b minus a x plus a plus b, such that a and b are real numbers. What we'd like to do, since it's a subspace, is be able to find a way to write it as the span of some vectors. So I'm going to write it as terms of a times something and b times something. You can take a little bit more time to write this out if you want, but in the end we'll get a times x squared minus x plus 1 plus b times x plus 1, where a and b are real numbers, and so we have the span of x squared minus x plus 1 and x plus 1. So remember, this is just a spanning set, not a basis yet, so we still need to show linear independence. So for basis must show linear independence. So let's do that. We take alpha 1 times x squared minus x plus 1 plus alpha 2 times x plus 1, and we set it equal to 0, which is the same as 0x squared plus 0x plus 0. I spell this out so that way it's easier for us to kind of make comparisons to the thing in front of x squared, the thing in front of x, and the thing in the constant term. So we get our system of equations is alpha 1 equals 0. We get negative alpha 1 plus alpha 2 equals 0, and we get alpha 1 plus alpha 2 equals 0. Okay, well, we know alpha 1 has to be 0. And if alpha 1 is 0 here, then we can combine these two. Normally we'd do a much bigger row reduction, make a show of it. But here we can kind of combine these to see that alpha 2 also has to equal 0. And so since we only have one solution here, since they both must be 0 and can't be anything else, since we have one solution, our set is linearly independent. So we have a basis. So the basis for v, which I'll denote b sub v, is going to be x squared minus x plus 1 and x plus 1. And our basis for m2 by 2, which is our basis for our codomain, is going to be the standard basis 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Okay, so now we need to take our basis elements and transform them using this transformation we have, and then write those transformed things with respect to this basis. All right, so what does that mean for us? We need to take t of x squared minus x plus 1, and then write it in terms of our basis for our codomain. Now, similar to the example in the notes, because we have these vectors from this domain as our inputs, we've kind of already broken down into what the a part is and what the b part is. So we have 1 times the a part plus 0 times the b part, and so we have 1 for a and 0 for b. Okay, that means using this transformation, we get 1, negative 1, 1, 1. And if we want to write that in terms of this basis for our codomain, that will be 1 times this vector plus negative 1 times this vector plus 1 times this vector plus 1 times this vector. If you don't believe me, I recommend going and see the coordinate vector portion of the notes from last week, and then kind of verifying this ends up working out so nicely. And then last but not least, almost last but not least, we need to transform x plus 1 and it in terms of our basis for our codomain. And so again, because we already broke down into our a and our b portion here so nicely, a is going to be 0 and b is going to be 1. And so we'll end up with a matrix of 0, 1, 1, 2, which we now will need to write in terms of the basis for our codomain. So this is coming from a being 0 and b being 1. So it will be 0 times this matrix, plus 1 times this matrix, plus 1 times this matrix, plus 2 times this matrix. And so in the end, our final matrix form is going to be 1, negative 1, 1, 1 as the first column, 0, 1, 1, 2 as the second column. And so again, if you can take an input for this transformation and write it in terms of a and b, you can multiply that a and b times this matrix, and you'll get a coordinate vector which you can use to put these 4 basis elements for the codomain together in order to get the proper output for the transformation.